think I finally got it. Alright, so I'll try to make these a bit quicker so people have time to actually review them, but we had said that we were going to look at some binary tree stuff this time, so let me swap over to the page where I put the repo, and I'll do everything from scratch here. So let's do, take that, start up the recorder, and let's go workspace, clone, into binary drive, and so the goal is going to be to, using the link here, make these trees, and then traverse them in the order that they're described over here. So we're going to write the code that's going to traverse a tree in the order that's defined in all of these different ways. I thought this would be a good topic relative to React, because under the hood, React is actually a big tree, and a lot of this stuff is actually happening. So if you were to look at React, when we have something like a view, or actually let's make it real. In React, we would have something like a div. Div would have maybe a child of like a p tag, and then this might have a div under it, and this div may have span, and so on. And that in React would look like div p that div maybe a span and then the question becomes, how does React navigate these hierarchies? How does it get from here down to here to render this one, to render that one, onto the web page? So we'll drop React for a second, and we will that's dead. Okay, make a new one. Here. So the goal with this one is going to be to make these unit tests that I had pre-planned pass. So I have the solutions already pushed to that repo, so I'm going to just roll back one and do it live. Here. Yeah. So this is the source that we have to implement, and binary tree test is the thing that has to pass. And you can make the test run by typing make live make test. This should have every test failing at the moment. Yep, excellent. So, okay, trees. There's lots of ways to make them, but we're going to take a simple approach and go for an object-oriented tree style. So trees are structures that have values and children. So if you look at a react tree, then if this is the tree, well, we have this tree up here. So this first tree over here has a value of div, and it has children has a p, and it has a div. There's the p, there's the div, and so on. So there's lots of little tricks you can do for trees too. Like for example, a tree is really an idea, and you may see some implementations of tree that attempt to use just arrays. So if we were to try to represent this React tree as an array, then it might look something like the first element is a div, the second one is the p, the third is the div, and then the p has no children. So we'll just say nothing for those children. And then the div has a span, and nothing else there, and so on. That's a little bit more complicated, so we're going to go with this simple value children approach, and we're doing a binary tree, so we'll just hard code the left and the right nodes. So here we started off. I'll use the interface that I subbed out in the source code file, which is binarytree.ts, which should be visible here in the src. Yeah, that file. So the value is going to be, we'll say a number. We'll just hard code the values of these things to be numbers. The left child is another tree, but it might not have one. The right child, similarly, is another tree. And we're going to want to make a tree like the one in the web page. So this is the whole definition of a tree. They're just recursive trees. So we'll make our tree is going to be equal to I'm going to basically hand transcribe this thing into our code. So the first node has 8, and the left one has a value of 5, and that left one has a value of 9, and 5's right child has a value of 7, and 7's left child has a value of 1, and 1 has no children. 7's right child has a value of 12, and that one has a left child with a value of 2. And 5 and 7, that looks good. So 8 has a right child with a value of 4, and that 4 of the right child with a value of 11, and that 11 has a left child with a value of 3. Somewhere I missed commas or something. The error is over here somewhere. Okay. Alright, so here's our tree. I'm going to copy that out into the test file, because that's where we'll be testing against it. And let's look at focusing on one of these methods first. Let's do pre-order. So pre-order is defined as going through the tree from 8 to 5 to 9 to 7, visiting the parent first, and then the left, and then the right children. So, given a tree, visiting the parent first, and then the left, and then the right children would be this one, then this one, then this one, right? 859, 859, and then the right, this one, and then this one. So, fortunately, the pre-order, post-order, and in-order should all be pretty similar. So let's make it, it's going to be a recursive function, so I might just make a little helper. Undefined the base case here. And then if we get a tree that's null, then we'll just say that there's nothing left to do. So this output array is going to be the numbers of the nodes in the order that it was asked for. And then if we have a tree, we'll return an array of the answer, where first you visit the parent, so tree.value, and here's the magic part. It's going to be everything from the left child, so that's going to be of tree.left, and then the right, and we want to make sure they're all just one flat array, so spread them out, and that should be over here, Oh, this point's kind of silly. We might as well just do it there. Yeah. And that should work. If I run this test, assuming I didn't mess up copying the tree in. Empty array. Oh yeah. So I don't want to use this null tree. I want to use the tree that I luckily called tree. Let's see if that works. Cool. And the other one should be really similar. I'll just here. Next we'll do in order, which is defined as the left child first, then the parent, then the right child. So that one's a little bit harder to imagine, but it should work pretty similar. If we had this, then this, then this, then that. So if we keep on asking for the left child over and over again, then we won't do anything yet, nothing yet, then here, and then there's no left child, so we'll get the parent, then we'll get the parent, then we'll get the parent, then we'll ask for the right, and then this one should be next, right? We're doing in order, left, parent, right, so it should be 9, 5, 1, yeah, 7, yep, cool. Yeah, then this one, and then this one. So that should be the exact same stuff, except over here in order. It should just be a matter of making sure we do this first. Yep. Left first. Then eventually we'll pop back up, get that parent, and then the preorder on the right. Oh, not preorder. In order. And find. Oh, and I have to get rid of this null tree. Cool. So next we'll do post order, which is also very similar. Get rid of that null tree. And we'll start with this implementation. And swap it so that the value here is last. That should work. Mess this up. Post order. And undefined. Okay. Okay. This one, level order, that's next. And that one is definitely the trickiest. It's commonly referred to as a breadth-first search, which is a question people often ask in interviews, for better or worse. So let's look at this one. So breadth first search. We have this style of search for traversing trees is a little bit different. All of these were forms of depth first searches, because we keep on going, we go deep, keep on prioritizing going deep. So we go down to here before we get down to here. Before we get to here, rather. But there's another category called breadth first. And that means, like it sounds, you go level by level. So you want to do first this one, and then this one, and then that one, and then that one, that one, and that one. And then you would keep on going in that way. So it's tricky because you can't just take the same recursive code and rearrange it to get these results. You have to do this two-pass approach. You have to first visit all of these things so you know which ones go where, and then finally take their values out and then return those. So we're gonna have a couple of lists that we maintain. So we'll have something like results array, and we'll have to be looked at. And the thing with that latter one is going to be, for as long as this list has something in it, we're going to take the very first element in that list and put its value in there. And then the job is to make sure that this list has elements that appear in the right order. So let's see how that looks. Get rid of that. So we have, we'll call it results, and this is going to be our number array, and this one will be, I'll call it queue because that's what everything calls this. We're treating it like a queue. We're enqueuing these trees to be inspected by us later. And this one will be of just the trees. And then while we have something in there, we're going to keep on getting the first one. Dot shift, I think. I always forget. Whenever I forget something like this, I just test it live. So there's a bunch of functions on arrays in JavaScript, and the names are terrible. So if I had 1, 2, 3, and I do a dot shift, then I get the first one, and it mutates the array. So okay, we'll just do that. It might be empty, even though it won't be empty, because obviously this is the check right here. But so if t, then so if we have something there, then we know it's in the right order, because that's what we agreed we'll do. So we'll say results.push, and that empties out the queue, and then the next two things that appear in the queue should be the children of the current node. So there may not be a left. That's fine though. That might actually be enough. The value. That could be enough. We can test it. Empty array. Probably something silly. Ah, yeah. So our queue is empty, nothing happened. So we should start off with the first node in the tree, which is tree. Nice. Cool. Yeah, so there's a, I think that's a good intro to binary trees. There's lots of other things that we could do with them, but I figured something short and simple might be nice for people to follow up. I think because the streams were so long, it was getting hard for people to actually watch them. So I want to see how it is to keep it like super short. So, all right, I'll post these notes, come up with something for next time, and hopefully it's useful. See you.